And now we go back to the form of Fourier transform now. So let's keep writing it. So because that's just not a whole lot of equation to write, because once we define this limit, like last time we defined the Fourier transform, I don't think that last time I don't use the language of the textbook. The language of the textbook, like use the Fourier transform called G, at least up to this section, it changed back to other notation. So G, in our notation, you use K, but you can go back now to the what the language notation in your textbook. So Fourier transform or function is now using a symmetric convention. Is f of d and e to the I over t dt. So that's the Fourier transform of a function f. And now at least up to this section, textbook use omega t, like t is a time and omega is your angular frequency. Okay, so that's definable. Then the inverse Fourier transform is like that, and we define this inverse Fourier transform just like a limit and a Fourier series, and you know that this involves defining the function just like what we did. So you can get the inverse Fourier transform this way. This is inverse Fourier transform, and using the symmetric convention, they are of the same form except this the sign of the exponential function. One is positive, the other is negative. Which one is positive, which one is negative is also a convention. Okay. For omega t, we usually put it this way. So in the inverse Fourier transform, we have a minus I. That's like the physicists like to do that. That common convention. But if you choose as a positive, then this will become negative. That actually doesn't matter that much. And if you use a wave number, usually we'll put a positive ik and negative ik. The positive ikx and dk, and negative ikx and dx. And so that is just notation wise. Okay. Now I think the next topic is just similar to the Fourier series. The Fourier series we define as, and then we this way, but then we talk about we can actually just use sine or cosine, define the Fourier sine series and Fourier cosine series. And for Fourier transform, is similar. There's some difference, like let's just erase something. So instead of talking about the infinite domain, so if you say now we start from, if you define a function, now go back to here. If you define a function that's only over a semi-infinite domain, so you start with a finite time. So these are finite. You always can define it as 2. And this function ft is only defined over positive t. Okay, we just consider the situation. And now, obviously, you can still use the original Fourier transform, because that ft is defined only of 0 to infinity. This means that you have a freedom to whatever this function is, right? There's a freedom you can choose what the f is at for negative t. So you could do that. You can just set f equals 0 for all negative t and put it in here. You get a Fourier transform. So obviously there's an ambiguity. You can whatever you choose for a negative value of f, you give a different g. but that doesn't matter that much as long as you put it back to inverse Fourier transform and consider t greater than 0 anyway. Then you still get the same, you still get back the same function, whatever g that you get. It doesn't matter that much. I mean, except that you don't put too much emphasis on the exact form of g, because that depends on how you choose your negative. Because if you choose it is 0, then it obviously is a discontinuity, and that discontinuity will contribute to some asymptotic behavior of this g, this Fourier transform as large omega. Obviously, because this is like the first steep variation that involve a lot of a lot of high frequency. We talk about this is a lot of high frequency mode because of the discontinuity. Okay? So, but as long as you go back to the same inverse Fourier transform, you still recover the same f this way. But that's one way to do it, and another way to do it, because we are involving just half of the axis, and we can either do it by reflection, just choose a symmetric function, just define when t is negative. You just define it as right, make it symmetric, right? And obviously, when it's symmetric, you put f a symmetric function in this integral g, and that is symmetric, but e to the I omega t involve cosine and sine. Cosine is even function, symmetric. Sine is odd function, is anti-symmetric. So f times cosine will be fine, and f times sine will be 0 after you integrate over the whole length. And when you integrate over the whole length the cosine function, you can actually say the integration from minus infinity to 0 and 0 to infinity is exactly the same, because they are this even function. You can say for in this situation, you can write g omega. That's just the cosine part, and then you multiply by a factor of 2, becomes 2 for pi. Now the integration from 0 to infinity, you have 3. Now you only keep the cosine term. And dt. Right. Okay. Obviously do that. Right. And the factor of 2, because we integrate, this original formula is from minus infinity to infinity, but because of the fact that this is symmetric over time, we refracted it, so the integration from minus infinity to 0 and 0 to infinity is exactly the same. Okay, so you understand it now. Okay, so that's how you get the factor of 2 out. So this is a Fourier. This is called Fourier sine, a Fourier cosine transform, right? Okay, I think the textbook called it as G sub C or something like that. Yeah, G sub C. Right? And obviously, you can also work out the inverse Fourier transform, inverse the only cosine. You just basically multiply, going back to your inverse transform. Now uh, G, now you can say that G omega is defined over only positive omega, right? And then uh, and then it's obviously this is because it involves only cosine, right? So minus omega is exactly the same as g omega, right? So g is also even in omega space. You only pick up the cosine term in this also. So ft for this case, the inverse transform is ft. Is likewise we integrate just half of that, so it becomes 2 to the pi. Integrate now is 0 to infinity to sub c omega when you pick up the cosine omega t dt d omega. This is inverse transform. Okay, so this is Fourier cosine transform. This is inverse Fourier cosine transform. Right, so that that's straightforward. Now another option, of course, you can, instead of going symmetric, you can go anti-symmetric. Now you just extend your ft over negative side by define a negative function. You can define f negative t over z. And now you could do the same thing. The Fourier transform now. This is now an odd function. So the cosine term is 0 after doing the integration. You have the I sine omega t that is give you a that will give you non-zero, and so this g omega, you can actually get rid of the I by always remember when you do the inverse transform. Also, you get rid of the I. Right? I mean, originally you have I sine omega t, right? But if you just get rid of the I in here, when you substitute, you also get rid of the I when you do the inverse transform that way. Right. And so you define the Fourier sine transform just the same way. But this time you multiply by sine only. Right. So now if you do define it this way, then you can add the 2 multiplied by I of 2. This becomes the full G. I mean, if G is definable this way. Right? Yeah. And so this is the Fourier sine transform, but then to do the inverse one, again, you put it back to the inverse formula, right? And now the inverse formula, remember we didn't get the I, so we need to put the I in here. And then again, this is an odd function. Sine is an odd function, so only pick up the sine term. There's a sine term have a minus I. This one actually has an I. You just didn't write it here, but when you put it back to you, that should be I. And there's a minus I sine. So I times minus I is 1. Right? So you get back to using this formula. T is T sub S. Okay, so there's a 2 options that you can have when you have a function that is only defined over a finite, a semi-infinite domain. Okay, and you just follow the Fourier transform formula and consider the individual cases. You get that. But it's something different from Fourier series. And last time we talked about over a finite domain, if you have a function, you can do all 3 transforms. As for all 3 series, you can do a Fourier series, Fourier cosine series, a Fourier sine series, and all these series are complete series, and they're all valid. So for this situation, Fourier sine and cosine is only defined over a semi-infinite domain. If you have a function that defines over the whole domain, then you cannot do either one of them because that function is arbitrary, may not be even or odd. So you cannot just simply do one of them. Because if f is defined over the whole T, then you cannot just do a Fourier cosine or Fourier sine series for that function. That is not definable because all this integration is over a semi-infinite domain, and you cannot cover ft that way. And no, but if you really want to just use one of them, for whatever reason, And we just realized that any function can be decomposed in a symmetric function and anti-symmetric function, right? You realize that any function you can just decompose it in symmetric one and anti-symmetric one, right? We can just say, right? So ft as you have a geometry, well, let's say we already used the H symmetric part. Since ft plus anti-symmetric part, right? And ft minus t will be equals to, changing it to minus will give you the same. Changing t to minus t for anti-symmetry will be minus. So just define h sub s as ft plus f minus t divided by 2. So h sub s ft is just 1/2 of ft plus f minus t, and likewise h sub a is 1/2 of ft minus f minus t. You can always define it. So if you like, obviously you separate as decompose the function as symmetric part and anti-symmetric part, and you use the Fourier cosine series for the symmetric part and the Fourier sine series for the anti-symmetric part. Then you can obviously still use this formula. I mean this formula, right? You can do that, but that effectively is just doing the full Fourier series, because exponential function is just involving cosine and sine. Like that, I mean, sometimes maybe that is useful, but this one, this is f as a function of t minus f value at minus t. You subtract the two to get anti-symmetric. And this is just show that any function you can always decompose it in an even function, odd function. It's just a addition of an even function and an odd function, right? And then how to get these two is just for using these two formulas, right? It's pretty straightforward to define that, right? Yeah.
Yes, composing this metric is what we have done.
What we have?
Okay, I'm asking.
Yeah. Yeah. Right.
That means
yeah, you can, once we do that, you can x sub s, you can use the cosine series, and the x sub a, you can use the sine series, because they are symmetric function now. This is symmetric, this is anti-symmetric. You can use the Fourier cosine series for this one, and using Fourier sine series for this one, because even if you use a full Fourier series, this one will only pick up all the cosine term, and the sine term will not give you anything. Because they're symmetric, you put it in here, the sine term doesn't contribute, right? Because now x sub s put in here, you only pick up the cosine part of the exponential function, right? Because this is, you explicitly define this as a symmetric function, right? Yeah, you need the sum now. You cannot use this. This becomes, you change it back to x sub a. X sub s is this one. X sub a is this one. Then you need to add the two. Okay. So effectively, you're going back to the full Fourier series, a Fourier transform, right? And, but I mean, just it's always possible to do that. It doesn't give you anything. I mean, it doesn't save you anything if you do that. But for the particular case that you define a function only over a semi-infinite domain, then you have freedom to use just Fourier cosine series or Fourier sine series, because you have an unknown part of the function over the other part, and you're actually free to choose whatever you want. Okay. All right. Yeah. So actually, in terms of textbook, we didn't go very far because your textbook it didn't actually explain that Fourier transform that in too much detail. So we need to add some of the background. Otherwise, it's just like formula. You should keep doing integral.